So usually vectors are free vectors, saying if you have a vector that's 3, 4, it could start anywhere, go 3 to the right, 4 up, and end there. But we have position vectors which fixes them in place. And it always fixes them in place with the origin. So here, position vector P means we go from O to P, where P is just the coordinate of a point. So when I'm talking about, when I write 3, 4 as a vector, it could be 3, 4 anywhere as a vector. But when I'm talking about a position vector, this 3, 4 specifically goes from 0, 0 to 3, 4. So if I had the point -6, 5, I could sketch the position vector P as -6, 5. And we could write it, I like the column vector, is definitely my favorite, but you could write it in terms of I and J, and you could underline I and J, or you could put arrowheads over top of I and J. Either of those would be possibilities. Resultant vectors. Now we're starting to get into the math of vectors. So if you consider the point 1, 3 and the point 4, 5, draw their position vectors. So this is my position vector from 1 to 3, and this is my position vector in green from 4 to 5. The position vector from A to B is the resultant vector. And this is where we get to have a little bit of fun with vectors and math and what makes vectors so powerful in doing math. Okay? So first of all, the vector A is 1, 3. Whoops, not with a fraction sign in there. It's sometimes hard to write numbers on top of each other without. And B, which is 4, 5, we could write as a column vector. Those would be the position vectors for A and for B. Now, if you wanted to go from A to B, how could you do that? Well, if I want to start at A and go to B, I could travel, like, in reality, if you were walking, you'd want to go directly there. But in vectors, vectors not worried about how long it takes to get there, it just wants you to get from one point to another. So I could start at A, I could go back to the origin.
Hi, do you also have Scott Grass?
I do.
Could I have him as well for a moment?
You bet.
Thank you.
I could start at A, I could go back to the origin, and once I got back to the origin, I could go to B. So how would I do that? Well, if this is position vector A, and I'll write it like this, going backwards would be -A. And then if I call this, I want green. If I call this position vector B, I could then add position vector B. If we write this mathematically, I would have -A, I'll do it in blue, A was 1, 3, plus green was 4, 5. Do you see that you get -1 plus 4? Oh, I drew the line again. Did you see that? So hard not to write brackets. -1 plus 4, that would give me 3. -3 plus 5, that would give me 2. And I get the resultant vector 3, 2. This is going to make our mathematics really, really easy for dealing with things in 2 dimensions and 3-dimensional space. Now, for me visualizing it, I like to think if I'm going from A to B, I'd first go back to the origin and then go origin to B. So I like to think of it as negative A plus B. Mathematically, often it gets written as B minus A just because it's easier to write out that way. Can you see that I could have done 4/5 minus 1/3 and got the same answer? But for visualization, it's much easier to say, I want to go from A to B, start at A, go back to the origin, that's negative A, then go to B. Technically, when it's written B minus A, here's B. You would do that first, to start at A, go B. And then here's a minus A. Minus A would be this way. Gets the same spot. Vectors work that way. Doesn't matter which one you do first. So if I do B minus A, I first go B, then I minus A. It's the same as going from A to B. Or I could first go minus A and then to B. Same thing. Now we're getting into some mathematics. Okay. What's really cool about this is that the resultant vector is really easy to find its length. A squared plus B squared equals C squared, right? Square root of 9 plus 4 will be square root of 13. And finding it that way, I think, is quicker than using your old distance formula that you had in grade 10. So, you can either write it this way, or that way, is perfectly fine. What's super cool is we can now apply this to 3 dimensions, which would be very hard to do with our old math. For example, I could ask you, there in 3 dimensions is the point A, and there in 3 dimensions point B. How far apart are they? And our first sense would be like, that's really complicated to try to draw that all out on paper and figure that out. However, I can just find the vector from A to B. Because my vector from A to B would be just B minus A. Or negative A plus B. And I do this and I got 6, negative 10, negative 3. And if you wanted to find the length of that, you could just do the square root of 6 squared plus 10 squared plus 3 squared. And you'd have its length right away. If that's A to B, B to A has to be exactly the same, but just in the opposite direction. So now it would be negative 6, 10, and 3. Now that we're working in 3 dimensions, it's like, technically we could say, oh, now I can do math in real life. Like, up till now you've been like on a piece of paper math, 2-dimensional math. This has way more applications. So if we know a vector PQ and PR, so we know this one in green, and we know this one in red. Then if you wanted to go from Q to R, you could go from Q to P, and then from P to R. Does that make sense that you would get back from, you started at Q and you would end up at R. So vectors work this way. You can always go from one point to another point and that point to the final point. And they're like, that's the same as just going there directly. Vectors aren't worried about how long it takes, right? They aren't worried if you're coming to math class directly from French class, or if you slept in and got your, you did get from your house to math class eventually. It all works out. So if x to y is 5, 4, 3, and x to z is 10, 0, negative 2, what's y to z? And what's z to y? Well, what we do here, so we can think about a picture. We have some three-dimensional space. It's kind of hard to visualize this, but I have some point y, which x to y is 5, 4, negative 3, and x to z is 10, 0, 2. Could I get from y to z? Yes. Can you see that you'd have to go from y to x, and then go from x to z? So y to z will be y to x and x to z, and very much like, sort of like in matrices, when those middle numbers are the same, they're basically going away, right? Y wants to go visit z, but first goes to x's house and visits with x, and then leaves x's house and goes to z's house. Did y get to z's house in the end? Yes. Happened to visit x along the way, but that's really not we're not worried about that. Now y to x is the same as negative x to y. So I can take y to x, change it from negative x to y. Now I got numbers to put in, and I can write my vector from y to z. And similarly, if I want to find z to y, it's just, if I want to find z to y, it's just negative y to z. Then I have negative 5, 4, and negative 1. I think this is where it'd be really cool if I had that three-dimensional teaching thing, so I could actually draw these vectors in 3 dimensions in space, and you could actually see where they were going. But it's pretty hard sometimes to visualize. Can you visualize 5, negative 4, 1 as a point? You're pretty good at visualizing in 2 dimensions now. Like if I said, think of the point 3, 5, you'd be like, yeah, it's quadrant 1. I have no problem seeing that in quadrant 1. But once you get that third dimension in there, it's a little bit harder to visualize. Okay. So now, in 3 dimensions, I have these 3 points. 2i minus j plus k, 3i minus 2j minus k, and 6i plus 11 minus 7k. We want to show that these 3 points in 3 dimensions are perfectly in a straight line. That's what we want to show. And I really like working with the column vectors. I find the math a lot less tedious than writing out the i's, the j's, and the k's, and different modes. So sometimes we think, well, what could we do in 2 dimensions that would work? How would we solve this in 2 dimensions? How would we then apply this to 3 dimensions? And there's a couple of different strategies you could use. One strategy is you could, does this make sense? If you found the distance from A to B and the distance from B to C, if they were in a perfect straight line, it would have to add up to the distance from A to C. Okay? That's one strategy. You could find the direction of A to B, and if it was parallel to the direction of B to C, they would have to be in a straight line, because as soon as they weren't parallel, it wouldn't be in a straight line. So there's more than one way that we can go about proving this, but we have to use sort of some logic first to say what would have to be true if it was a straight line, and what's not true if it's not a straight line. So if it is a perfect straight line, then the two separate distances have to equal the total distance. If it isn't a straight line, then A to B has to be parallel to B to C. And then we think mathematically, once we got those two strategies, which one's less work? Because mathematicians, we're lazy, right? We're like, yeah, that seems easier to do. So I'm going to figure out what the vector is from A to B, which would just be, right, there is some origin here. So I would have, I'd go negative A and then add B, and that would get me from A to B. Or easier, just B minus A. Same thing, I could figure out C to B. Are these parallel? If they're parallel, there is some number where one is a multiple of the other. And can you see that you could take the first one and multiply it by 3? Also in our explanation, it's important that you have this fact that they share the same point, because I could have two parallel vectors that don't share a point, and they're not in a straight, those 4 points then wouldn't be in a straight line. But because they share that common point in the middle, therefore, they have to be parallel. Do you see that you didn't have to use AB and BC? You could have used AB and AC, or BC and AC, as long as you chose two vectors with coffee stain or without. Jack gets coffee stain. Advantages of finishing first. So find a vector from A to B. So this is just going to be B minus A. And then once you've found that vector, its distance is super easy. Just the square root of each of the elements squared. We had this formula from the other day. Nice.